All right, so here's video 2. Now we're going to dive into the new stuff with the Hopital. I posted this again to start the video just to remind you that you have done these yesterday and you've handled those a little bit this morning as well with the warm-up. So today we're going to look at 3, 4, 5, and 6. Up front, 3 is going to be fine. 6 is going to be fine. The two that are going to give you not necessarily hiccups, just it might feel weird for a little bit, are these. Because remember, Hopital only works if you have a fraction. Well, on 3 and 6, you can make fractions pretty easily. On 4 and 5, the only way you can make fractions is if you log it to pull down that exponent. So we'll take a look at all 4 of these types in the next couple videos. Okay, next one is this. This is 58, so I thought I'd just try this one out with you guys. Limit as x goes to 2 from the right side of that whole thing. The first thing I do is I always plug in. When you plug in, you get 1 over 0 minus 1 over 0. And notice, normally, like when we talk about slope back in Algebra 1, when we say 1 over 0, we always say it's undefined. You got to realize, if this is 2 from the right, that means I'm plugging in something like 2.001. When you look at 2.0001 squared, you're going to get 4.00001 minus 4 is really like 0.00001. So when I say 0 here, in your head, you need to realize it's more like 0 points, a lot of zeros and a 1, and a lot of zeros and a 1. So it's not 1 divided by exactly 0. It's 1 divided by something super duper small. And notice it's super duper small on the positive side because I came from 2 from the right side, so it's a little bit bigger than 4. And a little bit bigger than 4 minus 4 gets you a little bit close to 0 on the positive side. And 1 divided by really small is super positively big. So here we get infinity minus infinity. Now, think back to those days on the elementary playground where it's like, I'm better than you. Oh yeah, I'm better than you times 2. Oh yeah, I'm better than you times infinity. Oh yeah, me times infinity squared. Oh yeah, well, I'm infinity and you're infinity and we subtract each other and we go away. No, you can't say that. Infinity is not a number, it's a concept. So even though you and I, our gut tells us infinity minus infinity is 0, we can't say that. We're just saying something huge minus something huge. I don't know. So we got to play through this. This is why it's indeterminate. Now, if I said a billion minus a billion, yes, that is 0. But if I say a super large number minus a super large number, I can't say they're the same number. So that's what we're going to take a look at. So on this one, it says, let's get common denominators. And I look at it and I go, huh, they already are common denominators. So I can just merge this and say, all right, we're going to do limit as x goes to 2 from the right of 1 minus x minus 1 all over x squared minus 4. Subtle difference. I don't have 2 separate things anymore. I have one thing. And the first thing we're going to do is we're going to plug in. Get 0 on bottom, and I get 0 on top. When I give a check like that, that means it's indeterminate, which means we can play with it with Hopital. So I'm going to do Hopital on this. And I'm going to take the derivative of both guys on top and on bottom. And before I would answer the question, I would merge it. I don't like this big tiered fraction, so I'm going to rewrite this as a 2-tiered fraction. So that's going to be 1 over 4x x minus 1. That bottom slides into the middle part when you would divide the fractions out. Now let's plug in 2 and let's see what we get. Plug in 2, I get 1 over 4 times 2 times 1, and that's 1/8. So visually, what this is saying is, at least I know this, from 2, from the right side, I'm going to 1/8. Okay, I don't know anything more of the graph than that, but 2 from the right side is going to 1/8. What we can do if you want is let's pull out our calculator, let's graph this thing, and let's look at a window to take a look at it. So I'm going to do that in a second. So I'm going to hit pause for a second, load it up, and I'll show you where that limit is. All right, so it's 7:47 in the morning after parent-teacher conferences where I got home at 8:30 last night. I'm exhausted, and I made a mistake on this one. It's a quick fix, but I'm glad I'm doing this on the calculator to show you so then we can see where my little negative mistake was. So I graph it. I have it here. I go in, and right now that's where you can kind of see why I'm alarmed, is if you hit trace 2, it should be blank because you really were dividing by 0. But just to the right of it and just to the left of it, it looks like it's a negative answer. And if you see, let me kind of point with my finger here, over there, it's 1/8. So somehow I'm off because I have 1/8 and the answer is negative. If you want to see it really closely, you can go to second table set, start at 2, be like 0.001, go to your table. And as I'm approaching from the right, it's going to negative 0.124, negative 1.247, 48, 48, 49, error. And so close to negative 0.125. So look at this, negative 0.125-ish as a fraction. It's negative 1/8. Okay? So it was approaching negative 1/8. Let's stare what I did wrong. Here it is, and I truly apologize. Being tired is not an excuse. I forgot to put that negative in there when I took the derivative up top. So right there, I forgot a negative, which means right there I forgot a negative, right there I forgot a negative, right there I forgot a negative. So it would be a negative right there, a negative right there, negative there, and make it a negative 1/8. So in my picture, let's see, I needed to have it pull down, and at negative 1/8, there's the thing. Okay, sorry about that. All right, let's take a look at the next type. So here's one where actually you need common denominators. They're a little bit different. If you plug in 0, you get 10 over 0 minus 3 over 0. Again, think not 0, but something really close to 0. That blows up to infinity. The other one blows up to infinity. We don't know if those cancel or not. So what we would do is we get a common denominator. I only need to multiply this guy by x. So I got limit, x goes to 0 from the right, 10x minus 3 over x squared. First thing I do is I plug in 0, and I get negative 3 over 0. Now, don't get in this Hopital groove where you just start taking derivatives. Is that indeterminate? No. You got to remember, that's negative 3 over a really, really small number. And when you plug in 0 from the right and you square it, do you agree that's a positive 0? Meaning it's something really close to 0, but on the positive side. Right there, that answer is negative 3 divided by something really small is negative infinity. So at 0, in that case, it blows down. So visually, and we won't graph this one, but visually, 0 from the right, it's going down. Do not take the derivative. You will mess up if you take the derivative and just keep going. So let me show you. Here's the wrong part that students do because they just feel like they're in a groove. Oh, let me take the derivative of top and bottom. I get 10 over 2x. Oh, let me just do it again without even looking. X equals, I get 0 over 2. Oh, my answer's 0. No. No. Do not just take derivatives for fun. I don't think you guys think taking derivatives is fun, so don't do it. Why do more work? Always check to see if it's indeterminate or not. All right, here we go. Here's a big one. Okay, so limit as x goes to infinity of that. Now, I already told you it goes in red to 1 to the infinity. So let's just look at that. 1 plus 1 over a huge number. 1 over a huge number should go to 0. So 1 plus basically 0 is 1. And 1 to the infinity. Now, just sit on that for a second as I take a drink of coffee and think 1 to the infinity, and that should bug you. 1 to any number. We've always said this. 1 to any number is 1. We've said it, we've said it, we've said it. We've always said 1 to any number equals 1. Okay? 1 to the 5th is 1. 1 to the 10th is 1. 1 to the 1/2. That's saying, what's the square root of 1? It's 1. What's 1 to the negative 3rd? Well, that just means 1 over 1 to the 3rd, that's still 1. So how in the world is 1 to the infinity not 1? Because the phrase, which is not a lie, 1 to any number, and this bugs you guys, but infinity is not a number, it's a concept. So all of a sudden, it's 1 to the yellow. What? 1 to the blue. What? 1 to the bicycle. What? 1 to the infinity. It's not, you can't just tell me what it is yet, because it's not 1 to the billion. And then now I know this bugs you guys. Well, 1 to the billion is 1. 1 to the billion plus 1 is 1. 1 to the billion plus 2 is 1. 1 to the billion times billion is still 1. So as I'm getting bigger and bigger and bigger and bigger, when does it become a concept rather than a number? That's kind of what your issue is. When does it become a concept rather than a number? I don't know. I just asked that question. That's a good question. I gotta sit on that myself. When is, what did I just ask? That was good. When does a number become a concept? I don't know. Man, I'm tired. All right, here we go. I'm going to rewrite this problem for you guys. I want you to think of this problem right now, as I'm still saying it's the same problem, but I'm going to say, what's the limit as x goes to infinity of y? Where y equals that. You guys agree it's the same thing? The limit as x goes to infinity of y, where y is that. Okay? So I want to just play around with y right now and say, let's look at y is this thing. And let's log this thing. So then I have ln of y equals x ln of 1 plus 1 over x. Okay? And my new question is going to be this. Find the limit as x goes to infinity of not y right now, but of ln of y. Okay? So the original question is that. That's what we really want. But we're going to solve this question first. Find the limit as x goes to infinity of ln of y. And what the goal is, or what the idea of this is this. Let's say the limit of x goes to infinity of ln of y equals 1. I'm making that up. Let's just say when we somehow can do this math, we get the limit as x goes to infinity of ln of y is 1. Now realize, I don't want that answer. I really want the blue answer up there. What is it for y? Well, here's the beauty of it. If you know that, then you can e this side, and you can just learn that the limit as x goes to infinity of y is now e. So the whole idea of it is, oops. Okay, that didn't work. I'm trying to draw. There we go. There we go. There we go. Okay. So our ultimate goal is to find the limit of y, but I do not know how to find the limit of y. So I'm going to find the limit of ln of y. Once I find that limit, I'm going to e it back, and then I'm going to get the limit of y. Okay? So how do we handle the ln of y limit? Well, right here, I'm going to pull this down, and we're going to start analyzing this. So right now, I want to find the limit as x goes to infinity of ln of y, which is better yet, the limit as x goes to infinity of x ln of 1 plus 1 over x. Right away, anytime you start with something, plug in first. And here I'm getting infinity times ln of 1, which is 0, and that is indeterminate, okay? Which is another weird guy, right? Because what have we always said? Anything times 0 equals 0. But we should phrase it, is it any number? Any number times 0 equals 0. And here's that whole thing again. 5 times 0, 0. 10 times 0, 0. 100 times 0, 0. Negative 2 times 0, 0. Yellow times 0. What? Yellow times 0? That's a word. What do you mean? Infinity times 0. It's a concept times 0. We don't know. Again, it's weird. Makes me a little wiggly, a little eerie. So, to do it, we always have to pull it back down into fraction mode. So, for me, I need a force of fraction. To force this fraction, I'm going to go limit x goes to infinity of, I'm going to keep the top guy ln of 1 plus 1 over x. But I'm going to divide. Now, I can't just say divide by x. That's a totally different problem because it really is x times it. But instead of saying divide by x, what about dividing by 1 over x? Now, think through that fraction. Dividing by 1 over x, that 1 over x, if you divided by that fraction, boop, it would pop up and the x would be on top. So I just kind of rearranged it. It's the same guy as the blue one that you're staring at. I just forced it into the fraction mode. And when I plug in that, I get ln of 1, which is 0, and 1 over really, really big, which is 0, indeterminate. So from that, I can Hopital it. So I'm going to do it in a different color to showcase the step. Let's see. Okay, stamp. Address the top. That's going to be negative 1 over x squared. Make sure you're okay with that because that is x to the negative 1. So negative 1 over x squared. And this guy, I'm going to get the same thing, which is kind of nice. And before I even try to figure out what that is, let's see what that merges to. That divided by that, that's going to be the limit as x goes to infinity of negative 1 over x squared all over negative 1 over x squared times 1 plus 1 over x. And what is nice here is those cancel out. So I have a 1 on top here. And I'm getting 1 over 1, which is 1. Okay. Now, remember, what did we just solve? We just found the limit as x goes to infinity of ln of y equals 1, which is it's kind of funny. That's what I kind of predicted up top in that big red box. So the limit as x goes to infinity of ln of y equals 1. I didn't want the limit of ln of y. I wanted the limit of y. So then that translates to the limit as x goes to infinity of y equals e, which is weird. It does not always happen. I don't want you to think this is always true, but 1 to the infinity, I'm pointing, but you can't see it. Let me point for you. Oh. 1 to the infinity does not always equal e. It equals e in this example that we did. It equals e. So when I say limit of for y, that's the exact same thing as writing the limit as x goes to infinity of 1 plus 1 over x to the x equals p, which we started with. Kind of cool. I have a little algebra 2 reminder here. Think back to banking, making money, interest, PERT, compound interest, interest daily, interest monthly, interest weekly, interest yearly, and stare at this algebra 2 reminder. That guy on the left was when we talked about daily, monthly, yearly, and that's what the N stood for. That N was saying how many times a year. The N was number of times a year. And then all of a sudden it went to here That's when n went to infinity. This is when it was compounded continuously. Okay? So realize this. Let's say instead of an r, let's say this was a 1, and then that would make that a 1. What did we just learn just in this last problem? What does that thing go to? What does that thing go to when n goes to infinity? That's the same. If you don't believe me, stare at it. That's the exact same guy as that one right there. Instead of an n, it's an x. And we learned that goes to e, which is that part there. In algebra 2, all we told you was, hey, the one on the left is for daily, monthly, yearly. The one on the right, for some reason, boom, 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 boom. That's continuously, meaning every single minute, second, millisecond of the day, meaning how many times are you making it? Infinity times. And it goes to E. We just proved that for you. Now you might say, no, we didn't. I have no idea what we just did on this crazy page. So we'll look at another one on the next video. So let's just set up the next problem. Okay. It's going to be this one. Limit as x goes to 0 from the right of x to the x, which is 0 to the 0. And again, we're going to practice this logging idea on the next video. So write this one down, start the new video, and we'll be analyzing it.